You've heard the word antimatter, and your brain immediately makes it science fiction. Spaceships, bombs, black glowing containers with warning labels. But antimatter is not a fantasy substance. It's real. It's been made in laboratories. It shows up in hospitals. It falls out of the sky in cosmic rays. And when it meets ordinary matter, it annihilates into pure energy with a neat, precise signature. So here's the question that sounds simple and turns out to be dangerous. Why does antimatter exist at all? Not how do we make it? Not what does it do? I mean, why is it part of the universe's rule book? Why isn't reality built with just one kind of matter? Why does nature bother having a mirror version of every particle with opposite charge? If you expect a story like God added a second kind for balance, forget it. Physics doesn't work that way. The real answer is stranger. Antimatter isn't an extra feature bolted onto the universe. It's what you get when you combine three ideas that the universe seems absolutely committed to: quantum mechanics, special relativity, and the fact that energy can turn into particles. Once you accept those ingredients, antimatter shows up like an accounting necessity, like the minus sign you can't avoid if you want arithmetic to be consistent. Now that would be enough if the universe were half matter and half antimatter everywhere, but it isn't. The universe around you is overwhelmingly matter. So the second question is even more unsettling. If antimatter is so natural, where did it all go? That's the real mystery. And if you want an honest explanation, we have to separate two problems that people mix together. Problem one, why does antimatter exist in the laws of physics at all? Problem two, why does the universe contain so much more matter than antimatter? The first problem is basically solved. The second one is not. Let's start with the part we actually understand. Take a charged particle you know, the electron. Negative charge, tiny mass, stable. Now imagine a particle identical in every way except the charge is positive. Same mass, same spin, same everything else. That particle exists. It's called the positron. It's the electron's antiparticle. How do we know it exists? Because we've seen it. We can create it. We can detect it. When a positron meets an electron, they annihilate and produce photons, often 2 gamma rays with a very specific energy, 511 keV each, because that's the rest mass energy of the electron or positron. That's a fingerprint. In fact, this is used in medical imaging, PET scans. A radioactive tracer emits a positron. That positron doesn't live long. It meets an electron in your body and annihilates. 2 gamma rays fly off in opposite directions, and the scanner detects them. A hospital uses antimatter as a routine tool, not a metaphor. Real positrons. So antimatter exists. Fine. But why should there be a positron at all? Historically, the story begins with a problem that looked purely mathematical. In the late 1920s, physicists were trying to describe electrons with a quantum equation consistent with special relativity. If you do non-relativistic quantum mechanics, you get Schrödinger's equation. It works beautifully for atoms, chemistry, low speeds, but it's not fully compatible with relativity. Then Dirac came along and wrote an equation that was. And when he solved it, the equation did something shocking. It produced 2 kinds of solutions for the electron's energy. Positive energy solutions, which make sense, and negative energy solutions, which look nonsense. Because in classical thinking, you don't have particles with negative energy that sit below everything else. If such states existed and were accessible, an electron could keep falling into lower and lower energy forever, radiating endless energy, and atoms would be unstable. Everything would collapse. Reality would be impossible. So what do you do when your equation predicts impossible stuff? You can throw away the equation. But Dirac's equation was doing something magical. It naturally predicted electron spin and the correct magnetic moment structure in the right way. It was too good to abandon. So Dirac did something bold. He reinterpreted the negative energy states. He imagined that in the vacuum, all those negative energy states are filled like a sea. And if you knock one out, you create a hole that behaves like a particle with opposite charge. That hole is the positron. At first, this sounded like a weird bookkeeping trick. But then in 1932, Anderson observed tracks in a cloud chamber that looked like an electron, but bending the wrong way in a magnetic field. Positive charge, same mass. The positron was real. So antimatter was not invented to make a cool symmetry story. It was forced on us by combining quantum mechanics with relativity in a consistent way. Now, you might say, okay, fine, but that's an old historical argument. Modern physics doesn't really talk about a sea of negative energy. True. The deeper modern viewpoint is quantum field theory. In quantum field theory, particles are excitations of fields. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. And when you quantize a relativistic field correctly, you do not get only electrons. You naturally get both particle and antiparticle excitations. In plain language, a relativistic quantum field has creation and annihilation operators for particles and for antiparticles. If you try to build a theory with only one and not the other, you usually break something fundamental. You lose locality, you lose causality, you lose Lorentz invariance, you lose a stable vacuum, or you get negative probabilities. The math stops making sense as a physical theory. So antimatter is not a bolt-on. It's part of the structure of a consistent relativistic quantum theory. Now we can make this feel less like math says so and more like physics demands it by thinking about energy and pair creation. You already accept a simple relation. Energy and mass are connected. E equals mc squared. That doesn't mean mass literally is energy in all senses, but it means mass can be created from energy and converted back to energy. We do it in particle accelerators every day. If you take two photons with enough energy and slam them together, you can create an electron-positron pair. That's not science fiction. That's a standard process. It happens near nuclei. It happens in intense fields. It happens in high-energy astrophysical environments. But here's the important part. You don't get just an electron out of pure energy. You get an electron and a positron together. Why? Because you must obey conservation laws. Electric charge is conserved. If you start with photons, which have zero net charge, you cannot end with a single electron, which has negative charge, because then charge would appear from nowhere. So the universe makes a pair, negative and positive, total charge zero. The same logic applies to other conserved quantum numbers in particle physics. When you create particles from energy, you tend to create them in combinations that keep the total conserved quantities balanced. So the existence of antimatter is deeply tied to conservation laws, plus the ability of energy to create particles. At this stage, the first question is basically answered. Antimatter exists because the universe is relativistic and quantum, and because it respects certain symmetries and conservation laws that make antiparticles unavoidable in a consistent theory. Now comes the second, harder question. If antimatter is so natural, why isn't the universe full of it? Because if the early universe made matter and antimatter in equal amounts, they should have annihilated each other almost completely. You'd be left with mostly radiation, photons, not much matter to build stars, planets, and people. Yet here we are, made of matter. The room is matter, the air is matter, the galaxy is matter. Where is all the antimatter? We do see antimatter sometimes, but it's tiny amounts. Positrons in radioactive decays, antiprotons in cosmic rays, small numbers produced in high-energy collisions. That's not half the universe. That's dribbles. So the universe has an asymmetry. More matter than antimatter. A lot more. How much more? Roughly speaking, in the early universe, there might have been about 1 billion pairs of matter-antimatter particles for every one extra matter particle. The pairs annihilated into radiation, and the tiny leftover excess, 1 in 1 billion, became all the matter we see today. Every star, every planet, every cell is made from that tiny leftover. So the question becomes, what produced that tiny excess? This is called baryon asymmetry, or matter-antimatter asymmetry. And to explain it, physics doesn't get to just wave its hands. There are conditions. In 1967, Sakharov pointed out that to generate more matter than antimatter from an initially symmetric state, you need three ingredients. You need processes that violate baryon number, meaning the number of baryons like protons and neutrons isn't strictly conserved in those processes. You need C and CP violation. C is charge conjugation symmetry, swapping particles with antiparticles. P is parity, mirror reflection. CP together is roughly mirror plus particle-antiparticle swap. If CP were perfectly conserved, matter and antimatter would be produced in exactly equal amounts in any process that starts symmetric. And you need departure from thermal equilibrium, because in perfect equilibrium, forward and backward reactions balance out, and you can't build up a net excess. Everything gets washed out. These three conditions are not philosophy. They are practical constraints that any successful explanation must satisfy. Now, do we see any of these ingredients in nature? Yes. We have observed CP violation in certain decays of particles called kaons and B-mesons. It's real. The universe does treat matter and antimatter slightly differently in some processes. Also, in the standard model of particle physics, there are ways baryon number might not be absolutely conserved at extremely high energies, and electroweak processes can violate baryon number in subtle ways. And the early universe definitely went through phases that were far from equilibrium as it expanded and cooled. So it sounds promising, but here's the punchline. The amount of CP violation we see in the standard model appears to be too small to explain the observed matter dominance, not by a tiny factor, possibly by orders of magnitude. That means either we're missing something in the standard model, or the asymmetry was generated through mechanisms we haven't confirmed, or both. So what are the candidate ideas? One big class is electroweak baryogenesis. The asymmetry is generated during the electroweak phase transition when the Higgs field settled into its current state. For this to work well, you generally need a stronger first-order phase transition than the standard model gives, and you often need new particles or new sources of CP violation. Another class is leptogenesis. In this idea, you first generate an asymmetry in leptons, like neutrinos, and then standard model processes convert some of that lepton asymmetry into baryon asymmetry. This is attractive because neutrinos are already weird. They have tiny masses, and their behavior may hide additional CP violation. If neutrinos violate CP in a big way, it could feed into the matter excess. There are also grand unified theories where baryon number violation happens naturally at extremely high energies early in the universe and creates the asymmetry. The problem is not a shortage of theories. The problem is evidence. So what evidence do we look for? We look for additional CP violation beyond what we already know. Experiments study rare decays, precision measurements, electric dipole moments of particles. If a particle has a non-zero electric dipole moment, it would signal new CP violating physics. People have been hunting for these signals for a long time because they would be a direct clue to why matter won. We also look at neutrino experiments to measure CP violation in neutrino oscillations. If neutrinos behave differently from antineutrinos in certain ways, it could be a crucial piece. We look at the early universe's fingerprints, the cosmic microwave background, the abundance of light elements, the large-scale structure. These constrain what could have happened. And we look for something even more dramatic, large regions of antimatter in the cosmos. Because if there were entire antimatter galaxies, they would annihilate at the boundaries where matter and antimatter meet, producing huge gamma-ray signatures. We do not see those signatures at the level we would expect if there were lots of antimatter domains nearby. That strongly suggests the observable universe is not a patchwork of matter and antimatter regions. It's mostly matter. We also directly detect antimatter in cosmic rays. But cosmic ray antimatter can be produced by ordinary collisions. High-energy protons hitting interstellar material can generate antiprotons and positrons. The key search is for heavier antimatter nuclei, like antihelium. That would be much harder to produce in ordinary collisions and might hint at primordial antimatter regions. So far, nothing definitive. So where does that leave us? It leaves us with a clean answer to the first question and an open mystery for the second. Antimatter exists because the laws of physics demand it when you combine relativity and quantum mechanics in a consistent way. It's not optional if you want the world we observe to be mathematically and physically consistent. But the universe's preference for matter over antimatter is still not fully explained. We have clues. CP violation exists. Out of equilibrium conditions existed. Baryon number violating processes may exist. But the complete story is incomplete. Now, there's a temptation here to turn this into drama. Science can't explain antimatter. Reality is broken, and so on. That's nonsense. Not knowing the final mechanism is not a failure. It's an invitation. It means there is more structure to discover. And there's something valuable about the kind of not knowing we have here. It's not vague. It's constrained. We know what ingredients are required. We know what signatures to look for. We can design experiments to test ideas. That's progress. Now let me bring the whole thing back to a simple picture you can keep in your head without turning it into a fairy tale. Imagine the early universe as an incredibly hot, dense bath of energy. In that environment, energy constantly becomes particles and antiparticles, and particles and antiparticles constantly annihilate back into energy. It's a seething equilibrium. For a long time, matter and antimatter are produced in almost equal amounts because the basic interactions are nearly symmetric. Then, as the universe expands and cools, the balance shifts. Certain reactions freeze out. If there is even a tiny bias, some tiny difference in how matter processes run compared to antimatter processes, then after countless interactions, that tiny bias can leave a small leftover. That leftover is everything. So antimatter is not the strange part. The strange part is that there is anything left at all. And that brings you to a deeper appreciation of the situation. The universe you see is not the natural outcome of matter existing. It's the outcome of matter barely surviving annihilation by a 1 in a billion imbalance. Now, if you're still stuck on why does nature allow antimatter, the honest answer is that antimatter is not a special allowance. It's the mirror bookkeeping that makes the rules consistent. Once you accept that fields are relativistic and quantum antiparticles are built in, and if you're stuck on why did matter win, the honest answer is we don't fully know yet, but we know the shape of the answer. It must involve those Sakharov conditions, and it must show up as measurable CP violation, or baryon number violating processes, or new physics in neutrinos, or in high energy behavior beyond the standard model. That is the frontier. So the next time someone says antimatter is weird, you can correct them in a useful way. Antimatter is not weird. Antimatter is normal physics. What's weird is that you exist in a universe where matter won by a tiny margin, and we're still hunting for the exact reason that margin appeared. And that should not make you feel disappointed. It should make you feel something better, that there is still something fundamental about reality that we haven't finished learning. Because that's what physics really is. Not a pile of facts, not a pile of buzzwords, but a disciplined way of asking questions that can be tested. Antimatter is one of those questions where the universe answered half of it loudly and clearly and left the other half as a whisper we're still trying to hear. If you want to play with the idea in your own head, don't just ask, why does antimatter exist? Ask things you can connect to experiments. How do we detect antimatter? Look for annihilation signatures like 511 keV gamma rays from positron-electron annihilation. How do we create it? Smash particles at high energy and let energy convert into particle-antiparticle pairs. How long can we store it? In electromagnetic traps, because you can't let it touch ordinary matter. How much of it is around naturally? Small amounts in cosmic rays and radioactive processes. How do we know the universe isn't half antimatter? Because we don't see the annihilation glow we would expect at matter-antimatter boundaries on cosmic scales. And what would convince us of antimatter regions? Discovery of anti-helium or heavier anti-nuclei in cosmic rays at levels inconsistent with secondary production, or cosmic gamma signatures that match boundary annihilation models. Those are concrete questions. They connect the big mystery to things you can actually measure. So yes, antimatter exists. It has to. Not because it's cool, but because the universe seems to insist on consistency. And yes, the universe mostly chose matter, not because it had to, but because something early on tipped the balance, and we're still working out what tipped it. That's not a comfortable ending, but it's the honest one. And if you think about it, it's also the most exciting kind of ending, the kind that means the story isn't finished.